Hey guys, my name is Mario, and just before we start, I want to say this is the first video I've ever done in my life, and I'm from South America, so English is not my first language, so sorry for any mistakes there. In this work for lab number 1 of physics, I'm going to analyze and observe a video of a car moving through pavement at almost constant velocity. For this, we're going to use Newton's second law, and we're going to try to prove how computing modeling with VIDLE and Python can help us understand and compare a real live movement in 1D. This is a car moving on pavement using tracker of the experiment. The total mass of this car is 106.84 kilograms. Its initial position is going to be 0.013 in the positive x-axis. On the right down side, we're going to see how position in the x-axis changes while time goes through. So this is what we're going to compare using our model. For this model, we're going to use VIDLE, in which we entered the object's mass, the object's initial position, which we got from tracker, the object's initial velocity, or VI, which we got using the first two positions and the 2 times which these positions happened in tracker. We're going to start in time, of course, 0. We're going to use 0.01 seconds as delta t so that we can do a good model, because as we've learned, if we use 2 large time spans for delta t, our module is going to lose exactitude. We're gonna Fnet is going to be equal to 0, 0, 0, since we're going to work in constant velocity. This part over here represents another way of saying of Newton's second law, which is our main principle or fundamental principle used, which is ball's velocity, or V final, equals V ball velocity, which is V initial, plus Fnet, which are all the forces exerted to the system by external forces, which is in this case 0, then the ball mass, which is not useful here because Fnet is already 0, times delta t. Finally, ball's position, which is R final, is equal R initial, or ball position, plus the ball's velocity, or the object's velocity, times delta t. When we run this module here, we're gonna get the following, which is and a straight line at constant velocity for the object. Now, when we use a spreadsheet to compare the model to the experiment, we're going to see a slight difference between them. This is because in real life, it is really hard to find real constant velocity because of all the forces exerted to the object. Probably the friction of the pavement on the car plus all the wind resistance was not exactly Fnet equals 0. But we can see that our model still works because it does a pretty good approximation of what happens in real life. As an extra comment on the video, I'd like to say that if we had changed the way of the axis, and value of the position would have definitely changed. So, as a conclusion, I would definitely say that computing modeling helps us see how real life movement D works. Although it's not really exact if you don't have enough information, especially when you're trying to use constant velocity, as it is not likely to find the net forces exerted by everything around your system to the system in 0. In this case, we can see in the actual experiment that the forces exerted to the car are not 0, and that's why, even though the model works, it's not going to be the same as the actual experiment in real life.